Greetings, differential equation scholars, and welcome to this additional video on the subject of the motion of spring mass systems. Here in this video, we're going to take a look at another example of damped motion and analyze it. So this goes along with section 5.1 and specifically section 5.1.2. We're going to take a look at two questions here. The opening question is, suppose that you have a 64-pound weight and it stretches a certain spring 3.2 feet. And suppose that that object is then set in motion in a medium where the damping force is equal to 16 times the instantaneous velocity of the object. The first question that we're going to answer about this is, what kind of motion are we going to have? Will we have critically damped motion? Will we have underdamped motion? Or will we have overdamped motion? We'll analyze the problem and decide which of those three scenarios we're going to be in. And then once we've done that, we're going to give ourselves some initial conditions. We're going to say that the object is released from equilibrium, right at x equal to 0, with an initial velocity of 1 meter per second in the downward direction. And given those initial conditions, we're going to find the equation of motion for the object. But first, we want to decide what sort of motion are we going to have. Since there is damping, is it underdamped so that the damping is not strong enough to overcome the spring's force, and we end up with oscillatory type of motion? Or is it overdamped so that we move smoothly towards the equilibrium position with no oscillation at all? Or might it be critically damped? So to help analyze that, we're going to find the spring constant for the system here. And once we find the spring constant and the mass, we will be able to use those factors to help analyze our first question. So let's take a look at our system here. And obviously we know that beta was equal to 16. That was the constant of proportionality for the damping. What are the K and the M for this system? So since the weight of the object was 64 pounds, and that 64 pounds displaced the spring 3.2 feet, we can use our Hooke's law, F equal to Ks, to find that K is F divided by S. It's 64 divided by 3.2. That comes out to 20 pounds per feet. That's going to be our K value. Now our mass can be found by using F equal to MA. 64 is equal to M times 32 feet per second squared. That's 64 pounds. And so solving for M is going to be 64 divided by 32 slugs. And that comes out to be 2 slugs in this case. So we have a mass of 2 slugs. And that means now that we can write our differential equation. M times x double prime plus beta times x prime plus k times x equal to 0. That's going to be our starting point for the differential equation. We substitute in our mass of 2 slugs, our beta constant of damping of 16, and our spring constant of 20 pounds per foot. And then we can divide by 2 to get a leading coefficient of 1 for the x double prime term. So our differential equation is x double prime plus 8x prime plus 10x equal to 0. Now in that differential equation, we want to make sure that we are identifying what our omega squared is and what our lambda and lambda squared are. The omega squared, remember, we've known that since back in section 5.1, that's k divided by m, which here is 20 divided by 2, or 10. 10 is omega squared. 10 is omega squared. What's lambda and what's lambda squared? Well, remember that the coefficient of the x prime term here, once we have kind of normalized the equation and got a leading coefficient of 1 for the x double prime term. The coefficient of the x prime term is twice lambda. So 2 lambda is equal to 8 here, and that means that lambda is equal to 4. Okay, and also remember 2 lambda is always equal to beta divided by m. So if beta is 16 and the mass is 2, that means that 2 lambda is going to be equal to 8. So we've got lambda equal to 4, and that's going to mean that lambda squared is 16. So now let's take a look at what that means for our type of motion. Now that we've established that omega squared is 10 and that lambda squared is 16, well, we can answer our first question with that. We're going to take a look at lambda squared minus omega squared and see what the sign of that is. Remember, the 3 scenarios are that if lambda squared minus omega squared, that's essentially the discriminant of the radical in the quadratic formula. So if that difference is negative, then we're going to end up with complex roots, and that means we're going to have an underdamped situation where we will have some oscillatory motion. If lambda squared minus omega squared is positive, then we'll have 2 distinct real roots. That'll be an overdamped situation. There'll be no oscillation. Smooth motion towards equilibrium position for the object. And then the special case where lambda squared and omega squared are exactly equal to one another, where their difference is 0, we call that our critically damped situation. So which one of those situations do we have here? Well, we know that lambda was 4, so that lambda squared was 16, and we know that omega squared was 10. Their difference is positive 6. Because that difference is positive, that means that we are in this situation right here. We are in the overdamped motion scenario. This will be a non-oscillatory situation. We won't have sines and cosines as part of our solution function. We will have an overdamped situation. Now that we know what to expect, we can take a look at what the exact equation of motion will be for the particular initial conditions that we had mentioned earlier. Let's take a look at those now. The differential equation x double prime plus 8x prime plus 10x equal to 0 has an auxiliary equation of m squared plus 8m plus 10 equal to 0. That quadratic equation has 2 real roots, and we knew they were going to be real because of our earlier analysis. They turn out specifically to be -4, that's negative lambda, plus or minus the square root of the difference of those squares. Remember, just a minute ago, we found that the difference of the squares was 6. So negative lambda plus or minus the square root of lambda squared minus omega squared. Here, that's -4 plus or minus the square root of 6. That means that the solution to the differential equation is going to take the form e to the negative lambda t, or e to the -4t, right here, times c1 times e to the square root of 6t plus c2 times e to the minus square root of 6t. That t class there should be up in the exponent. That's a little error there. Put that t up in the exponent for the second one. Now, when we get the initial conditions, when we apply them, x of 0 equals 0, x prime of 0 equal to 1, when we substitute in those values, we're going to find out that the initial condition on the position tells us that the sum of C1 and C2 has to be equal to 0, meaning that C2 is the negative of C1 and vice versa. And we also find this condition here from the initial velocity. Since there was initial downward velocity of 1 meter per second, that's positive 1 in our orientation system. That gives us this constraint that -4 plus the square root of 6c1 plus -4 minus the square root of 6c2 has to equal 1. We'll do a little bit of algebra. We'll solve for c1 and c2, and we'll find that c1 is square root of 6 divided by 12, and that c2 is negative the square root of 6 divided by 12. Since we essentially have, since those are just opposites of one another, I'm going to factor that out and write that expression at the beginning of our solution. Our final equation is the position of this mass will be the square root of 6 divided by 12 times e to the negative 4t. That's at the beginning, our damping term, times e to the square root of 6t minus e to the minus square root of 6t. And here at the end, we've got that t where it ought to be up in the exponent. That's our final solution. This is our equation of motion for this overdamped situation where our lambda squared minus omega squared was a positive value. Hope this video has been instructive and another good example to chew on for solving problems involving damped motion. Stay tuned, coming to a YouTube channel near you will be another video on section 5.2 dealing with boundary value problems.